Today's outcome on static electricity is you will be able to ask and answer questions about statically charged objects by reading text and making simple observations so that you can identify the cause and effect relationships which create the charges. So watch the student as she writes down the slide. Why do you think this happened? What other places have you seen this happen?
In this presentation, we're going to review forces. We're going to explain the difference between contact and non-contact forces, and we're also going to develop your understanding of what electricity and static electricity are. So what exactly is a force? Well, very simply, a force is just either a push or a pull. And hopefully you learned about this in kindergarten when you did your pushes and pulls unit and you built a windmill. But even if you didn't, you should know that anytime you force an object, you give it a push or a pull. And that's what causes motion. To make an object move, you need a force. So what are some different kinds of forces? Well, some forces require contact. And that's just a fancy term for touch. Some forces are a result of objects touching. One of those examples would be friction. Friction occurs anytime two surfaces or two objects rub together. A classic example of that is when you rub your hands together. If I rub my hands together, there's a lot of friction. It's harder to move my hands than if I was just moving my hands without actually touching. There's a lot less friction when I'm not touching my hands together. More friction, less friction. You could try that. You can actually feel the difference. So that's one example of a contact force. Another example of a contact force is if I were to actually push or pull something by making contact, by pushing it. Some forces don't require any contact. They don't actually require any physical touching. So we call them non-contact forces. And so while some of you may know Star Wars and the Force, sorry Finn, we're not going to use that kind of a force. Some actual real-life non-contact forces would be magnetism, electricity, which we're going to explore in this presentation, and gravity. So check out this video. Look at that thin piece of metal. It's being kept up in midair. No one's touching it. What do you think could be keeping that thin piece of metal floating up in the air? Well, if you thought magnets, no, there are no magnets. It's got to be something else. There's got to be some other non-contact force keeping it up in the air. What do you think it might be? So let's explore electricity. In order to understand electricity, we have to understand particles and the charges that they have. So for what we're going to explore, there are two types of particles. There are negative particles, and we can see that minus sign inside that circle. Now scientists call negative particles electrons. There are also positive particles, and you can see that plus sign inside of that circle. And scientists call positive particles protons. Now, it's not super important that you remember that negative particles are called electrons and positive particles are called protons. You just need to know that those different particles interact or behave in different ways around each other. Why is that important? Well, because the way that those particles react to each other or behave around each other, that helps us explain a lot of the things that occur in our world. So let's start by asking some questions. What do you think will happen if I bring a negative particle and another negative particle together? How do you think they'll react to each other? Well, let's see. Wow, when I brought that negative particle close to the other negative particle, it didn't want to be anywhere near it. It pushed away from it, and we call that repel. Because like particles, a negative and negative, they don't want to be together, so they repel, they push apart. Interesting. Well, let's see what happens when we bring different particles together. What happens if we bring a negative particle and a positive particle together? What do you think will happen? Well, let's see. Wow, something totally different. This time when we brought a positive particle and a negative particle together, they stayed together. That's because opposite particles want to, what we call, attract. They want to pull together. Similar charges, like a negative and a negative, they want to repel. They want to push apart. Opposite charges, like a negative and a positive, they want to come together. They want to attract. So let's see if you can figure out this third one. What do you think will happen if I bring a positive particle near another positive particle? Let's see. Did you predict that it was going to repel, that it was going to push apart? If you did, good job. So let's just review. Opposite particles, okay, negative and positive, they're going to attract. They're going to pull together. Similar particles or like particles, like negative and negative, or positive and positive, they're going to repel. They're going to push apart. So now that we understand particles and how negative particles and positive particles react to each other, what does that have to do with electricity? Well, there are two types of electricity. The type of electricity you're probably most familiar with is the kind of electricity that flows, the kind of electricity that's moving around. It's the kind of electricity that when you flip on a light switch, the light comes on, or when you plug something into the wall, it'll turn on, or it'll charge your phone, or whatever. And so that kind of electricity, current electricity, is a result of something called an unbalanced charge. That's when those negative particles are flowing. In this example up here, you can see that there's a battery, and it has a negative and a positive end. And what happens is those negative particles, those electrons, are going to flow from the negative end of the battery through the light bulb, which makes it light, and then it's eventually going to flow into the positive end. Because remember what we said, opposites attract. So the negative flows to the positive. That's current electricity. That's electricity that we're most familiar with. But there's another kind of electricity that's called static electricity. Now, what's the difference? Well, static electricity doesn't flow. There are still negative particles, and they're still going to be moving, but it's a one-time move. Because what happens is those negative charges build up on a surface or on an object, and they want to move, but it only happens one time. So static electricity is an unbalanced charge, and it's when negative particles build up on an object, and they can only move one time, unlike current electricity where they just keep flowing. So let's explore static electricity a little bit more. How do we get a static electric charge to build up on an object? Well, some objects are much easier to get a static electric charge built up on it than others. One of the classic examples is if you have a balloon and just your hair, because the balloon will very easily accept some of the negative particles, and your hair will very easily give up those negative particles to the balloon. So what happens? Well, let's look at this diagram. First, right here, we see that there's a balloon and there's a person's hair. And you don't have to count it, but believe me, there's an equal number of negative and positive particles in here. And what that does, that means that we have a balanced charge. And so all those particles, they're happy because particles like to be balanced. They like to have an equal number in whatever object they're in. So that means there's no charge. Okay, it's a balanced charge. It's not negative, it's not positive. Overall, the balloon and the hair have a balanced charge. So what happens next? Well, if we were to take that balloon up against this person's hair, she has a lot of hair, by the way. If we were to rub it up and down, what will happen is the hair very easily can give up its negative particles. And so they transfer over to the balloon, which can take those negative particles. And so that's the second thing. We have to have some actual touching. And so what happens is those negative particles transfer from the hair over to the balloon. So what happens next? Well, the problem with that is now there's a lot more negative particles in the balloon, and there's less negative particles in the hair. And so that means there's an unbalanced charge. This balloon overall has a negative charge, and the hair now overall has a positive charge because the particles are out of balance. Well, remember what I said earlier, those particles want to be balanced. So what's going to happen? Well, think back to what we said earlier. What happens when you have a negative and a positive? What do they want to do? That's right, they want to come together. And so what happens, if you bring those close together, they want to pull together. And that's how static electricity works, and that's why when we bring those together, we can even get a shock, because the negative particles want to go back into the hair so that there's a balanced charge.
Lightning flashes in the sky, creating a sudden spark of electricity. One of the most powerful phenomena on Earth, lightning throbs with several 100 million volts of electricity. Although lightning bolts are less than 2.5 centimeters wide, they are capable of heating the air around them to 30,000 degrees Celsius. That's 5 times hotter than the surface of the sun. At any given moment, there are 2,000 active thunderstorms on the planet. Lightning strikes Earth between 50 and 100 times a second. There is definitely electricity in the air. But while lightning is beautiful to watch, it can turn deadly if you're in the wrong place when it strikes. Scientists are not yet able to accurately predict where and when lightning will strike, but they do know that it usually strikes tall, pointed objects such as trees and buildings. That's why so many buildings have lightning rods on top of them. Lightning rods are made of highly conductive metal that provides a low-resistance path for the electricity. When lightning strikes, a wire attached to the lightning rod carries the electricity safely to the ground. A lightning display is an awesome sight, but it is safer to admire it from a distance. What is the function of a lightning rod? As you watch this segment, think about what causes lightning and what path it follows when it strikes Earth. Lightning is one of nature's most beautiful and powerful displays. It is a spectacular example of static discharge. But much is still not known about it. To understand lightning, it is important to first learn how it forms, and that begins with thunderclouds. Thunderclouds form when moist air from Earth rises. As the moist air rises, it cools, and as the temperature drops, condensation occurs, producing drops of water. The droplets are pushed upward to the top of the cloud and spread horizontally. Thunderclouds are able to reach heights of 10 kilometers or more, about the same altitude that some passenger jets fly. Fast-moving winds reaching speeds of up to 30 meters per second help to expand the thunderclouds upward. These winds cause the water crystals to be in constant motion, resulting in lots of tiny collisions. These collisions cause the upward-moving particles to lose electrons, giving them a positive charge, and resulting in the top of the cloud acquiring a positive charge. The lost electrons gather at the bottom of the cloud so that the bottom of the cloud acquires a negative charge. Eventually, the buildup of electrons and resulting negative charge at the bottom of the cloud becomes so intense that electrons at Earth's surface are repelled by it and are forced deeper into the ground, resulting in a positive charge on the ground immediately below the cloud. When this happens, electrons in the negatively charged cloud jump to the positively charged ground, resulting in a spark, lightning. Only about a third of all lightning strikes occur between the cloud and ground. The rest occur within and between clouds. But how is the bright spark of light we see created? A lightning bolt starts when the negatively charged underside of the cloud sends a stream of electrons downward in a jagged path. As the negative stream approaches the ground, an upward positive discharge starts from Earth, which is very difficult to see. As the two charged streams come together, they create a pathway for a powerful electrical current to begin flowing. That's when lightning occurs. This discharge of current is nature's way of trying to neutralize the charge separation between the cloud and Earth. And why does thunder coincide with the flashes of lightning? The air around a lightning bolt is superheated to about 30,000 degrees Celsius. This sudden heating causes the air to expand faster than the speed of sound. The expanding air cools, then contracts. Quick expansion and contraction of air around lightning starts molecules in the air vibrating back and forth, making sound waves. Although we know how lightning forms, we still cannot predict where or when it will strike. But the scientists at the Langmuir Laboratory are working hard to change that. Atop Mount Baldy in New Mexico, at an elevation of almost 3,353 meters, this lab is in an area with some of the highest occurrences of lightning in the United States. Here, scientists take advantage of the electrically charged location by triggering lightning and attracting it to hit specific spots. They do this by launching rockets into a lightning cloud that has such a high charge that lightning is unavoidable. When the rocket is struck by lightning, a charge follows a wire that is anchored to the ground. The wire serves as the pathway for the lightning bolt. From this research, scientists are trying to learn more about lightning, how to predict where and when it will strike, as well as arrive at a deeper understanding of the full scope of its power. Until then, it is best to admire these powerful bolts from a distance while scientists continue to try to understand this beautiful phenomenon.
So let's learn a bit more about static electricity by doing a couple of simple experiments. For this first one, you're going to need a straw, a plastic bag. I like this one from Chick-fil-A. Take it right out of the sleeve there. And now what I want to do is I want to rub that straw with the plastic bag. Once I rub it with the plastic bag, I'm going to bring it close to the yarn and watch what happens. The yarn is attracted to the straw. So what do you think caused that? What changed with the straw? Or what changed with the yarn? Let's try this with something a little different. I'm going to go into my bathroom here and do the same thing, but I'm going to use the straw on a small stream of water. Now, the trick to this is getting a consistent stream of water, just a small trickle, but it's got to be a solid stream. If it's a little drippy, it really won't work that well. But go ahead and you rub the straw again with the plastic bag and watch what happens. I'm going to show you close. I'm not touching the water here. The straw isn't touching. Watch. Now, I'm not claiming to be the Avatar, but check that out. I'm a waterbender. Really puts a nice bend into it too. Isn't that crazy? Look how kind of angle is that? That's amazing. And now for the last experiment, I'm going to need a balloon, my trusty plastic bag again, and I'm going to try the straw as well. Even though the straw is not part of the experiment you have, you can try that. And I'm also going to use some paper dots from a hole punch. Now I'm going to rub the straw with the plastic bag and the balloon with the plastic bag, and watch what happens. When I get close, watch how the paper dots react. Okay. So now we're going to try that again with the straw and see how it reacts. Again, rubbing the plastic bag on the straw. Acts just like the balloon did. Now I'm going to try rubbing the balloon against my hair instead of the plastic bag and see if that gets a different reaction. Look, stacking straight up. Oh, and there was one paper dot left. Yeah, the paper dot's gone now. And we'll try the straw. Now, I did not use that straw. That's a clean straw. So let's see what happens if I try the balloon that's been rubbed in my hair. How will that react? Ooh, there's a different reaction than we had before. I wonder what causes that. Why does that work better than the plastic bag? What's the difference? Even the straw that I rubbed in my hair has a difference to it as well. Seem to bounce up and bounce off. Try different materials and see what kind of reaction you get with your experiment. So let's review what we learned today. So we definitely asked and answered questions about static electric charges. And if you use the paper packet, you read some text as well. And we made a lot of simple observations of the different ways static electricity is produced and the effects that static electric charge has on the objects that it's affecting. So as you continue throughout the week, look for examples of static electric charges around you and stay curious, my friends.